It's my pleasure to welcome Professor Reza for today's talk, to give today's talk in our winter seminar series. Professor as well is the Herbert C. Sadler Collegiate Professor of Engineering at the Department of Naval Architecture and Marine Engineering here at the University of Michigan. And he comes to Michigan after being faculty at Virginia Tech for a number of years. He's now been here for 2 years in Navy. And Professor as well is an expert in marine renewable energy. And the uniqueness of his work is he goes from concept to large scale work. And he's mentored numerous students, is very prolific in publications. And I'll mention a couple of his awards, one of which is a Energy Design Award from ASME, and the Leonardo da Vinci Award, also from ASME. So without further ado, Dave, the floor is yours.
Okay, thank you. Thank you so much, Professor Maharsh. Very pleasure to come here to talk. Here I mostly talk big picture about my vision and what's the next step about the modern energy side and the political economy. And so for not sense very broad, not that detailed to compare with several seminars and in the past. Okay, so and before I talk about modern energy, I want to give a little bit of background about me, and you will get confused why I'm in this department. Okay, and first I finished my bachelor degree in automotive engineering. So then 1999 I come to MIT, and at that time master degree I get 2 master degrees, one in electrical engineering and mechanical engineering. I work on the vibration, like lithography vibration, and work on the electrical side. Then in summer, I went to GE. I did an internship there, worked with the multidynamics, just get big steam turbine, jet turbine. Then I returned to MIT, finished my PhD degree on the NICO project. It's basically vibration isolation. And the NICO project is 2017 Nobel Prize. The guys used to detect a gravitation wave. So we built a big vibration isolation system to detect the microwave, gravitation wave, the distance induced change, 10 power 21, negative 21, okay. So 10 power negative 21. Okay. So then I went for, after finishing my degree, I went to work in a pharmaceutical company in Chicago. So in Chicago, in that time, I work on the robotic system, something like that, something benchtop chemical reactor, and some project like a brain signal recording, neuron signal. Then I returned to university, first day and slowly broke, and then Virginia Tech, then Michigan. So wow, all the experience, right? Why I'm here? Okay, so I'm going to say okay. And when I come back in 2012, I work on the vibration energy halving and electronic system. And then I was center director, like Virginia Tech Energy Halving Center. Then I come here, okay. And then my lab was Marine Renewable Innovation and Education Marine Lab, okay. So you see my background, right? Car and vibration control, ocean dynamics, electronics design. Okay, so here we talk about marine energy, fluid flow like that. And this picture shows the blue color. Okay, marine energy using whale, tidal, and ocean current, river current, ocean wind, even biomass side, right? Given the fact that human beings only act on 30% of that, right? 70% of water, there's huge resource we could use. And take ocean whale example, right? Whale along US side, in US coastline, it can power whole country or whole country. Consider the tech economic feasibility and consider tech, especially this is for the technical feasibility side. Okay, we can get 1/3 of electricity for ocean whale. And the potential is huge, right? and the density is not. And this figure shows the density, the measured in kilowatts per meter, okay? And so in the west coast, we can have 20, 40 kilowatt per meter. Here, 10 to 20. In Greenix, about 0 kilowatts per meter. What that mean? You sit in the beach, the wave propagate to you 1 meter length the power. And if you look into the square meter, right? If you put a device, 1 square meter device, you put in the average, you can get from 2 to 3 kilowatts. That is from Fanny's the pioneer in his published paper. Okay, so and you compare with solar, right? Solar you put in the sun, and the sunlight is about 1.5 kilowatts per square meter. You have efficiency, right? You have a couple watts, or couple hundred watts per square meter. Or I want to say, wave energy is 10 times. The density is 10 times more than solar. Okay, so and United Nations and defined the decade of ocean science for sustainable development. Okay, so and this European Union's vision about blue economy, right? Blue economy basically sustainable use of the ocean resource, right? So it includes all local sense, including marine transportation, right? Include the fishery and aquaculture, and also the alternative energy from ocean wave, ocean current, right? Biomass, and this type of thing. And the United States, U.S. Department Energy vision, powering for the economy, right? We can get energy from ocean, and we can power underwater robot, right? We can power fish farm, and we can power seawater mining. We can power isolated community, and we can power water desalination for fight for the disaster, right? And so, and let us say the ocean wave energy. There's this first patent in 1799, right? And it's in France. So for 100 years, and there's no much progress. In 1940s, Japanese researcher, they use ocean wave energy to power the lighthouse. So ocean wave energy is driven by the oil price, right? When 1970 energy crisis happened and 2000 energy crisis, now there's another peak, right? And this energy crisis drive people to think what the alternative energy, right? And ocean wave come to the vision, and people. So this number of people per year published, okay. But you can say they started 1970s by 2008, and it's already on auto papers. Now, 1 year, you can probably find 2,000 people, and you can get a sense how many. Just imagine every day 3 new papers, right? So this gives you a sense about wave energy research side more energy. So 2008 was an important year, and not because I come back to university, it's because 2008 DOE first. DOE is the first corporate proposal of ocean wave energy, and they invest $9 million. And 2016, so DOE creates water power technology office. So with a budget 45 million. And this figure gives you a sense about the spending, right? And 2024 last year is 141 million dollars. And in the first 10 years, and this data, okay, they have put 38% of the money to support industry, 1/3 to national lab, or 1/4 to university. And after 2008, I feel they invest more to the national level side. Okay, I don't have data for that. Okay, so even you add together how much we spend, right? So however, now if we talk about ocean wave energy, no one knows what's that about. is different from wind energy. If we say ocean wind, if wind energy, you have all big towers, 3 blade. Now you have no idea. The reason is there's no research convergence. And there are so many concepts. And so one paper said, they said 250 concepts. And another paper, they said they did survey more than 1,000 concepts. And so no one know which one best. There's no criterion to judge which one best. So, or not widely accepted criteria. Different people present different way. Okay, this is one type of wave energy converter. Think about buoy, right? The buoy move up and down, right? And in the ocean wave, this buoy drive a generator through motion transmission, so for the particle, and then get electricity. This is then we deliver to the end user. So you look like that. You have wave energy, mechanical energy, electricity, end user. You need 3 critical or 4 components. One is the wave capture structure, another particle machine to convert energy and electricity, another one you need control to coordinate everything. So it involves all kind of engineering challenges. However, engineering is not only one, and like the environment, economic, society, policy, the community, right? So ocean wave energy, and it need really, really multidisciplinary research. So this is why I'm here, right? You see my background, I have dynamics, control, electronics, and even machine design, right? So I want to take my background and in this multidisciplinary area to make some contribution in the ocean energy. So that is what's going on here. I come back to university in 2008, first work on the cost extension energy, conversion and control, and civil structural turbine vibration like that. Then 2010, and I realized, wow, this core building that vibration is usually on the odometer, and we will the amplitude like 7 seconds, 5 seconds, 10 seconds, very close to the ocean. So I started looking to ocean. So I first work in state funding, later get some federal funding, build a prototype, tested in the ocean in 2014. Later, I get some funding from DOE, right? I mentioned DOE 2017, they started the office in park, water park technology office. We get funding to build 100 kilowatts device. And later, we also designed for 100. We did a test that in the real ocean. And because it's 100 kilowatts, it's 40 meters, 50 meters, very large device. So, and then later I have some other research in collaboration with European countries. And we are going to also say some research how I take advantage of pharmaceutical industry experience to drive energy research. Okay, so then I looked into the parabolic economy 2029, the DOE's vision about how to use energy power sensing in the ocean. I started this research on it because in 2015, I developed a wave energy converter to power ocean communication and also power water desalination, later fish farm and remote island like the ocean monitoring, right? And I also look into ocean current energy and ocean wave and offshore wind. So that is the work I'm doing. I select several projects I want to highlight quickly. And as I said, give you broad vision, what kind of things are going on. So, and I mentioned 2008, I come back to university 2010, I read a paper written by Professor Bartow. Professor Bartow, he was the former president of Portugal Academy of Engineering, and he built the first Europe Union's wave energy converter that connect to grid. Is on Peak Island and 400 kilowatts wave energy converter. Okay. His converter look like that way. They will move up and down, drive their turbine to in and out. And this is special turbine, where's turbine to drive the generator into one direction motion. Okay. When he reviewed this paper, in this review paper, he said power takeoff is possibly single most important element in wave energy technology. What power takeoff? Power takeoff is the machinery that convert the mechanical energy into electricity. Here is a Wells turbine, right? And another thing like this, human beings first trial of a wave energy farm in 2008 in Scotland. They built this device during the wave motion. This drive the hinge. The hinge drive the piston, and piston drive fluid. And the fluid they have accumulate high pressure accumulator, low pressure accumulator. Here they use check valve. In this check valve, they convert the bidirectional motion into single direction rotation, right? And the device is so complicated, it operates several months, is totally failed. So they designed for 2 megawatts farm. Okay. So no matter this design or this design, you can say they want to have generator single direction rotation, right? Wheel is bidirectional rotation motion. Okay, it can be horizontal or can be vertical. Okay, so now and this is how I bring my skills in the design side into the field and build such kind of prototype. I show you first, then show you how it works. Okay, so you can say this will move up and down, drive the buoy, and we generate energy to power the night, right? And so what's inside here, this move up and down, then drive or not, move up and down. Okay, then let us take a look at here. So just imagine the way you drive up and down. Take a look at the generator, right? And generator here rotates in one direction. So no matter this move up and down, this always rotate one direction. So the design actually is very simple. And everyone ride a bike, and we use two one-way clutch, similar to your bike gear, right? And in one direction, it's direct drive. In this engage, direct drive, right? Another and so another side is this is very compact compared with the hydronic system, right? And another thing is flying usually the inertia, which hurt our control. Now big systems better because it acts as a small and capacity. So, and then we build these prototypes. We test the 5 meters offshore in the ocean. So then later we also get chance to build and 10 kilowatts device. And this me and this generator, this gearbox here, as well as 50 kilowatt power electronics system. Okay, so we get efficiency and 80% for this small scale design and irregular wheel, and this is some sort of drive, irregular wheel, and we get a 37 to 60%. Okay, so this is wave energy converter side. And I mentioned that there's some advantage. Another advantage I will show you about here. Okay, so this typically vibration system drive in the ocean, right? And here this is a modern side, mechanical domain, electric domain. So for the wave energy converter, it's based on vibration system. What you want to do is measure the frequency, match the damping, electric damping and mechanical damping match, right? And for ocean wave, and usually the frequency is very, very low, is about 0.1 hertz, right? And when you put this buoy in the water, typically the frequency is very, very high. It's hard to match, right? This one side. Also, ocean wave is a very, very broad frequency. In the broad frequency, what you will do, typically in literature, people use nonlinear spring. And the nonlinear spring here, you take this modern side, right? And you optimize this system like this, you will find most time the spring is zero. And how to use nonlinear springs not possible here and in between, right? So I would say possible, but it's not practical. People still look into possibility of nonlinear spring here. Here we introduce another concept of nonlinear mass. And what does that mean or nonlinear mass? Okay. So you have this move up and down, right? By direction, you drive the flower into one direction rotation. Clearly, by direction into one direction is nonlinear, right? Another thing, instead of mass, we say inertia. Inertia means when you move this up and side down and there's a force. The force is proportional to the rotation inertia. And however, it's relative for relative acceleration between this end and this end. So it's called inertia. So with this nonlinear mass, we can make the broad frequency energy conversion, like two mass system. You can imagine that way there are two resonance, right? So now we increase the mass, we get a broad frequency. Another thing is damping and drag damping. Here, as you can see, this damping effect, okay. And if we use smooth streamline shape, right? We can decrease the drag, then the energy we can get a little bit more. So that will give you a sense how we can use such nonlinear dynamics and also hydrodynamics to improve the power output. So then in thermodynamics, okay, so wave energy converter, okay, I said it's a vibration system. In this vibration, there are three unique terms. One is mass, right? Mass is added mass. What's added mass mean? Your buoy move up and down. The water surrounding the buoy is move up and down also. Such kind of kinetic energy corresponding to the added mass. And the second part is radiation damping. When the buoy move up and down to generate the wave, will propagate out and wave energy loss from this buoy. So this is radiation damping. Or third is excitation force, right? You will come in excitation force. And all these three unique terms are frequency dependent, right? You have different way to model that time domain, frequency domain. Time domain, you use convolution term to describe the frequency dependent term. And the excitation force is non-causal term. You need, if you set into yesterday's the seminar in mechanical engineering department, right? Jeff Sprague asked the faculty candidate about non-causal. This means excitation force here. Anyway, and all this thing, when you design that, you design this PTO stiffness, PTO damping. You also can choose different mass, second mass. And this is the result we can get, okay, the power output. So if for the single buoy case, that is this case, right? Or a two body case, right? And you have different mass ratio. You just imagine that way, if mass is very, very tiny and this move together, you don't have energy output, right? And if this mass is very, very large, you will get a single buoy case. And in between, there's the best ratio of this mass ratio, okay? And this best mass ratio, what happened? Actually, there's physical meaning. Physical meaning is still match frequency. The only thing is, at this time, the spring is stiffness, this part is zero, right? We talk about damped natural frequency. And one of the damped natural frequency match excitation frequency. Therefore, we get resonance. At this resonance, another is motor shape. The two move out of phase. That means when buoy move up, this tank move down. It generates relative motion. This relative motion get energy more output. So, and this tank test, and I want to show you this one, you get a sense what I said, relative motion. So this is connected to the tank, right? And this is buoy. You can see clearly out of phase motion. Because it's out of phase motion, and the power output side can be much more than the single buoy case. So this is okay. we talk about that PTO is the most important element. However, you put there everything in the water, you have to consider all the things. And from wave source to the structural dynamics, hydrodynamics, power electronics control, right? And this is SME mechanical magazines highlight all our work. Okay, so overall, we care about from wave to wire efficiency, basically from wave input to mechanical system to power electricity output. We have to consider everything. So, and so the shape is important, right? Shape is related with capture width ratio. Capture width ratio is how much power input and how much power convert into mechanical energy, right? So it depends on the hydrodynamics design, the shape design. For example, this reference model 3 that has been used on auto plates, and they have added mass through this plate, but this plate will introduce on auto damping. And here we use streamline shape, we can increase the power capture ratio by 2 times, right? Overall efficiency, and here we get about 20% from wave energy to electricity. Okay, so this is power output, the time domain. Or another thing you can say, the peak to average ratio is very, very large. So you want to have average that has 1 kilowatts, and then peak can be 15 kilowatts. This is what I mean. Okay, so there's disadvantage. So you want to make the peak average ratio small. The reason is the peak force corresponding to how large your device is, right? It's about money, right? Average energy is the sense about economic benefit. Okay, so in addition to that, we also did the power electronics control, right? And here you just imagine that way, this generator, there's an internal inductor resistor, right? Here, this is 3-phase and AC to DC converter. Instead of use diode, we use controllable switch. Another thing is, now this inductor become part of the AC to DC converter. So then we can control the switches and achieve impedance matching. Okay, we talk about impedance matching. Okay, and this part we have inductor, right? The inductor, if you want to have resistor to match this part, and this part have to complex conjugate this part. So as a result, you have to use pretty large resistor, right? In the large resistor, we can use this control to achieve and cancellation of the inductor effect. We'll take advantage of this inductor for the AC/DC converter part. Okay, here this is experiment study. Okay, you put a resistor here, right? Maximum you get 10 watts, and here you use the power electronic side in the tank test. Okay, we can double the power output. So what I want to say that the electronics and is important part. So that is still suboptimal control. Why suboptimal control? In this system, we only consider the impedance or the dynamics of the generator side. We didn't consider the power, the buoy, the dynamic side. And in that sense, the energy will go to one direction only, right? So now we talk about control side. Okay, why control usually we mean active control. Sometimes you take energy out, sometimes you put energy back. However, you have one-way clutch. With one-way clutch, will hurt us. Why? You just imagine the way you ride a bike, flat road is no problem, up here, no problem, down here, lost control. The reason is your pedal cannot control the wheel, right? And similarly, when you put this system here, this is generator, right? Upper side is buoy, right? Your buoy can drive the generator, generator cannot drive the buoy, right? Therefore, we cannot use control. So active control. In electric domain, what we are doing, okay. And what we are doing is we change this semiconductor diode into transistor. this diode, this transistor, right? And now this transistor, we can use voltage or current to control the switch on and off. This is active synchronized electric rectifier. Now, can we change? We can create something in mechanical domain to achieve such kind of active motion rectifier. And in that way, the generator always rotate one direction. The generator can control buoy go to up or go down. That's the way. Okay. So in this, we achieve active control. Okay. How we do that? I mentioned I have a car background and I borrow another element in the car. Okay. And this electromagnetic clutch, right? In the car, there are two clutches. One is a manual car, you use manual clutch. Another is electromagnetic clutch, like you starter, not starter, also air conditioner. When you push a button, you engage the compressor. Okay, this electromagnetic clutch. Here, we use two electromagnetic clutch to achieve this function. So I didn't go through the video, what I mean. And this means if this get engaged, the drive here, and if this move another direction, we can go through this path. In that way, we can always maintain control instead of loss control, right? So this is another project we work on. As I mentioned, this is 100 kilowatts wave energy converter design. So, and in addition to the active motion rectifier, another innovation and the dual flap side. This video shows the result. You have single flap and you see almost no motion, right? Rotation. Here, the dual flap, the wheel is same condition, you have large motion. And in that way, and the Morin 9 force will be small. And here, if you can fix this Morin 9, right? And fix the button, you will see large motion. Now, we can use a smaller Morin 9 floating design will be there. Okay. So our third innovation here is about PTO game. And for example, here, if you have flap rotate, and given the frequency so slow, right, 0.1 hertz, and if this flap rotate 30 degree, you can calculate the RPM is about 2 RPM. It's very, very small. You look like your watch is 1 RPM, the second, right, pointer. Now, the 2 RPM, your generator, you need at least 0, 100 RPM, right, for what you will do. And you have to put a mechanical engineer. I say it's easy, right? It's just put gears. Yes, you put gears. What happened? Efficiency loss, right? The torque increase. As a result, you have make your gear very, very bulky, right? So what do we do now? This is design, okay. And instead of using put a gear, this, so, or you put a huge generator, right? This company, and they put 5 meter of generator. So when this generator initially tests in the dynamometer in area, they cannot get into the room because too large. So anyway, so let us say our design, we put this generator here, and we put arc. So during the arc motion, and we have belt, right? This look like arc is like large pony, this small pony, right? In that way, we can significantly magnify the motion, right? So this is one you will say, right? The flap motion drive the belt, and drive another small pony. As a result, this is a very small motion, we can quickly increase the speed, right? So we don't need another gear. Another thing, everything is in the air. You don't maintenance, everything will be easier instead of putting it in the water. So, and we finished this design for make the target at the ocean test in Pacific Pacific wave side and in construction in west coast. Okay, DOE invest $100 million to build the test site. Okay, this is we design for the test site. Okay, so we do multi-scale design. Basically, we did full-scale system design first, look into hydrodynamics, right? And then we build 1 to 10 scale small device and test validate in a tank. And I also design the active motion rectifier PTO side. And we did 1 to 2 scale PTO, and 4 scale is 100 kilowatts, or 1 to 2 scale is 5 kilowatts. Anyone can tell me why it's not 50 kilowatts? There's no, okay. And so if you know a fluid, you know the scaling law, right? The power and scaling is 3.5 times, okay, from the scaling law, okay. So we test this is in ongoing, actually in area right now, and we'll complete this month. And then we have third party like IBS did the design review for us, give us feedback about structure integrity and FEI analysis to say any potential damage like that. Okay, so we also implement the control side. This is in collaboration with the Sandia National Lab. And now the control become two parts. One is control the switching. I told you two electromagnetic current, and also control the generator torque. And this system identification, frequency response, right? And then we design the loop. And overall, I want to say the active motion rectifier compared with the traditional system, we can double the power output 2.4 times. Okay, so I gave you one example, right? We are excited about a mechanical motion rectifier. Later we find this problem we cannot implement control. The reason is we did the design in series, not in parallel, right? Ideally, when you design system, we need to consider everything from structure side to the PTO side to the control, everything together. This is the control core design, right? Or a certain core design, engineering system, control core design, you put the controller as chief engineer to take everything, right? Now, and the optimization people say, okay, I have multidisciplinary optimization, right? So I call the engineering core design, okay. So engineering core design, what does it mean? Okay, so you have, for example, this flap type of wave energy converter, not full, okay. And here you have the hydronic system, you have electromechanical system, then you have generator like that. If you consider everything in the modeling that, you call this mechanical impedance like this part, and this is also impedance here, generator part and control part. Okay, now control core design means you design all the mechanical system, you have maximum power output, right? And maximum power electric output doesn't mean you have the maximum electric input. For example, or a lot of people say, okay, you have swing set, right? You push that, you always same direction. Or you design the hydronic system so that the force is in line in same direction of velocity. That is actually mechanic input. You have maximum mechanic input. However, if you have some dynamics in the system, which introduce the phase difference or introduce a damping like that, and you maximize the electric input, and your electric output may not be best. Therefore, the true core design, we highlight output side. We design every element and all the controller so that the voltage and the current in phase, instead of here velocity and force in phase. So, so I want to say that I worked in the pharmaceutical company for 4 years. Okay, pharmaceutical research progress, right? Usually, for example, COVID happened, right? Then they identify some protein or whatever tissue that can that attacked by the virus, right? The target, right? Then they screen all kind of compounds, millions of compounds to say which one can interact with target. If we can interact with target called heat, right? After that, then they do certain optimization and dancing, that's a need. Eventually, we go to a couple of drug can go to clinical trial. Clinical trial is very, very costly, right? So now, what's the relationship of this and our wave energy researcher? Okay, so this totally different. A lot of wave energy researcher, right, and a company, you have some technology, you fail a patent, right? You want to say, okay, the technology I want to commercialize, I want to use the wave energy, the technology driven. Pharmaceutical industry is not technology driven. And it doesn't mean, so, okay, one guy invent one compound, I want to make a drug, right? You wouldn't do so. It's totally different. That is more like market pull approach, right? You identify the need, you look into the solution, right? And a lot of technology-driven company, especially wave energy company 10 years ago, most of the company 10 years, well, then they finally drive everything into the ocean. Once they put it in the ocean, everything failed, and the investors withdraw the money, the company shut down, right? The technology-driven mode. And we need to use the pharmaceutical-based design to know the research convergence. Okay, the idea is like that. Okay, we, instead of our engineer to create something, we give to the community, ask the end user to use or convince them to buy your solution, right? We're going to work together, and engineers and the user communities and environment scientists, society, social scientists work together to drive the convergence. Basically, now we identify some market, for example, remote community like the Beaver Island, what they need, right? Then based on what they need, we downstream all kind of concepts. Then we develop criterion to evaluate the concept. And then just a couple of things we test in the tank. This is more like clinical trial, and then go to the ocean or water test. So this is research convergence. We have new project we work on this one. So specifically another previous small project, we work with the Beaver Island to drive the research convergence. Okay, so now most of my research, let me say, our research also cover some part. Now I go through the part very quickly, like water desalination. Basically, we have wave energy converter power, hydronic pump, hydronic flow, and go through the membrane side, get fresh water. So that is the test we did in the tank. And here, this out fresh water come here and brine come here. And this figure to show how it works. The piston pump drive that everything to the high pressure side. And so we can use energy to produce fresh water, and we can use fresh water to produce food, right? So another thing, consider food. There's also seafood, right? Nowadays, more than half of our seafood are from aquaculture, right? And so the idea in this project is funded by USDA. And we did a survey about US agriculture. They found two most important things. One is the fish farm clean, and another dead fish removal. If fish died, if you don't remove bigger fish, bigger animal will come here, damage the net. So, and currently they use diver to do this work. And instead of use diver, we want to develop a robotic system like that. You have the energy from ocean and use that to clean that. So, and this is for the wave energy converter. There's a special design here. We use a cable driven PTO, right? So the cable move. This is prototype we built. This move up and down, and then this drive the cable. The cable drive the generator like that. So we did a tank test again like that. Students built this and the test lake. So We also work on the offshore wind energy side. In terms of offshore wind, the most important thing is the platform, right? And the platform compared with land-based is the motion vibration. So idea here, we use vibration reduction. This vibration reduction, like tall building, I mentioned my first federal funded project, how to harvest energy from tall building, right? This tall building in earthquake or wind, this big ball is put there to reduce the vibration. That is called a tuned damper, right? This vibration like that. So because it's small mass, the vibration get reduced. Now we put this small mass inside the floating platform, then to generate out of phase motion to reduce the vibration. So, and this is tank test again. There are some uniqueness. I mentioned the inverter, right? Instead of tuned damper, this tuned inverter damper, and we can significantly reduce the mass to half. Okay, as I mentioned, type 1 that is 600 tons mass. You just imagine that way you can reduce to half. So, well, we also have ongoing project use vortex-induced vibration, reduce the subsea cable. Subsea cable contribute 80% of the energy loss. The insurance data, the insurance companies' data, okay, they said 80% of the claimed loss because subsea cable. Subsea cable vibration is important. Vortex induced vibration. We collaborated with UIUC and NREL work on the solution. It's more like a nonlinear tuned example for this vibration reduction. So we have one project to reduce the noise in the pair driven. Pair driven, just imagine the way this can be 10 meters, right? You have huge hammer to hit that and then to generate noise. The noise can kill all this fish, right? So now we use metal material in the water and metal material in the seabed to reduce the vibration. So we have to acknowledge that US marine energy really behind the other countries, including Europe, even some Asian countries. Therefore, we have a lot of collaboration with European countries. And in the next 3 years, every year we can send up to 8 students, send them to European countries. And they stay there summer, we pay them airfare and pay them salary like that. And last year, we also need to take all my students to Taiwan, and this we pay the students to travel or whatever like that. Okay, so on the education side, and I put my lab education in my lab because education is a very important part. One part I want to highlight is professional skills, right? And we usually train our students very well in technical skills, but we didn't teach them well enough in the commercialization, entrepreneurship, public speaking, leadership, whatever like that. We hope that we can train our students with soft skills, okay, or professional skills. And so we also created the Go Blue Center, right? And it's industry university collaborative center with site in Stevens and in Texas. Okay, this is we most work industry driven project. So basically industry gave us funding to work on the problem. And we have multidisciplinary team, including Professor Asha Seren here too, okay. And here, overall, this is what's going on in the group, right? I mentioned that and on the hardware side, and I didn't talk too deep in each topic area, right? So I want to draw a conclusion. So there's huge energy potential available from ocean, right? And we need a really not multidisciplinary research to make that happen. And the playground is not enough, and everyone can find something to do, right, on the topic. We need to keep our eye open, keep our mind open, and have to acknowledge our knowledge is limited to handle things in the ocean. We have to accept other people's idea and to think, acknowledge our idea may not be right or even totally wrong, right? Open mind collaboration. We need to train our students not only engineering skills, and also we need to teach them social science, teach them business professional skills. So, and here, again, my team is relatively large, and I have actually I should update. Okay, half a certain scientist. Okay, one left. Okay, and 4 postdocs, 9 PhD students, 4 masters, and I have quite a few projects we need students on postdoc. I want to quickly highlight one is design, and this is signal project and funded by NOAA. We want to design something that can harvest energy from wind and wave, use it to power green lakes. Green lakes, you put a buoy there, wintertime cover with snow, right? So, and it wouldn't work. And then, and this design work, this ocean monitoring, this small buoy design, wave energy side. And another thing is the dynamics and control. And we are in the process, DOE provide us $1 million to design hardware local system to test things in the lab, right? Need control. And we also have project, and we design the modern system, modern observer side. And this one, when I talked with Professor Maharsh, I said, okay, we can have one postdoc work on this hydrofoil project, right? And this hydrofoil, the two look like similar. What's the difference? Actually, they are totally different. This one is more like kite, right? Basically, you use cable when the ocean wave is surface wave, deep ocean, right? And quarter wavelength deep, right? 20 meters or below, there's almost no wave motion. So the idea is here, more like kite. And when the wave drive this buoy move up and down, give the force. This force drive this kite to move. This similar to here, right? So this is different. This is for the shallow water. Shallow water, the wave drive provide propulsion force. It's similar as how the whale use the whale to ride the whale to drive front. So the two look like same, but the mechanism hydronic side are totally different. Okay, and I will hope some of you guys can join us look into this program, and Professor Maharsh has been nice to give total support on this project, but I still didn't identify right person on that yet. Okay, so I stop here. Sorry for taking longer time.
For the energy extracting device, how far out from the shore do you have to take it in the ocean?
Okay, and it depend on the water depths, right? And also depend on the device. For wave surged plate, the type of thing, the energy we most generate energy from horizontal motion. So shallow water would be better. In deep water, the wave is circular. Shallow water is like that.
Yeah,
Right.
so that was my next question. So does the orientation
Okay,
matter?
and yes or no, for flat, the orientation matters, right? And just imagine the wave will drive here and will drive this direction. And we did some simulation, plus or minus 30 degrees, the wouldn't change. You will change 45 degrees, the power significantly reduced. Okay, however, you put a buoy in the water, it doesn't matter. The wave come this direction, will come this direction, right? This is called a point observer because it looks like a point, doesn't matter which direction.
So would it make a difference if, so right now, as I see, both the devices are restricted to only 1 degree of freedom, either horizontal or just vertical. Would it make a difference if you had like 2 degrees of freedom? Like they could both go up and horizontal, depending on where you.
Yeah, you can design such kind of thing. Yeah.
are there any? I'm
I saw such kind of design and it's not very successful. Yes, PTO is already very complicated, right? So,
and you also mentioned a couple of.
Let's go around. Yeah, see if somebody else has questions. and we'll come back to
okay,
you. Yeah.
yeah,
Any other questions?
yes.
I have a question about the control design part. I might miss some detail, but I'm wondering that when you do the control design, I think it's more important to focus on the mechanical design, or like if it's more important you have a better control algorithm. Like I'm interested.
When I say control algorithm,
Cause yeah, I'm interested in like,
Yeah.
when you do like, it is like PID is still like the most dominant way to finish all the goals, or you have MPC or non.
so let me say that way. And we look into MPC too, right? And PID or needle leg, the type of thing.
Yeah.
And the even adaptive control probably have very good application here. Okay, so and the MPC, the design and the best of MPC, if you tune the PID parameter where the performance very close. Yeah. So let me say that way, wave energy control is different from traditional control. Why? And just imagine that way, I give two examples. One example is like all not vibration system, right? You want to make your vibrations smaller the better, right? Basically, you want to make it small, but wave energy, you don't want this sense become small. You want to make it larger, right? This side, if you look into control theory, you know RQ control, linear quadratic control, right? You have gain matrix R, Q, N of diagonal term. Mostly RQ control, you don't care about off diagonal term. You just say diagonal term. For wave energy control, you don't care about diagonal term. You care about off diagonal term. Off diagonal corresponding force, time, velocity, right? And diagonal term like x square, u square, the corresponding to x square means motion amplitude.
Yes.
U square is the force, right? Where is x square times u square? We care about off diagonal term, totally different.
I see.
Yes.
Okay.
So with the wave glider design that you showed, is the goal to generate power by embedding generator into the system or just to generate thrust?
So let me say that way. There are two purposes. One is drive, right? And we want to drive the system by wave only, right? And another thing, generate energy. Once we drive into a certain location, we can change this control, make the closed, right? We don't drive the system. Now, when this buoy move up and down, the cable now drive this generator, right? So we want to do two purposes. Here we put a cable here, right? And we can even put this hydrogen in this system, whatever like that, right? And this can become autonomous rescue. You need delivery electricity, you need delivery hydrogen. I put in this to navigate to your place, right? So similar here, two functions. One is propulsion. Another thing is energy harvesting, right? You know, some boat, they just use passive hydrofoil to drive, right? They will drive them, move them around. So this one is close to the ocean surface, therefore it's more like the wave and interaction with that. This is in the deep water, therefore it's more like kite. When you pull that, it moves. Which one is best? I don't know. So,
Maybe Anshu, do you ask your question?
just like definition wise, how are you defining your, you mentioned a couple of efficiencies earlier, that one system was 80% efficient and then the other system. Are those efficiencies defined based on the energy of the wave?
Okay, efficiency, if you look into wave, there are two parts. One is a capture width ratio. Capture width ratio is wave energy input and mechanical energy output. So however, wave energy input is calculated, not really wave energy input. It's just okay. They have 10 kilowatts per meter. You have 1 meter, they have 10 kilowatts, right? And so that is not really efficiency number. Sometimes people say hydrodynamics efficiency. That's misleading because wave capture width ratio can be more than 1. So the reason is you have buoy here, whatever like that, will come in. You think all the energy come from that here, but the 1 meter buoy, you say 1 meter times 10 kilowatts per meter, right? You say 10 kilowatts. However, this wave energy from this side can get into this system too, right? As a result, your output mechanical energy can be 1.5 kilowatts. So anyway, so this wave capture width ratio, and you can roughly understand or this, although the concept is not right, hydrodynamic efficiency. Okay, another is mechanical energy to electricity. That is another efficiency, PTO efficiency. Or this time together will be overall will to wire efficiency.
Thank you.
There aren't any more questions. Thank you very much, Rick.
Okay, so thank you.